right, hello everybody. My name's Bryce Virgin, and I'm here to finish the second part of my talk on quantization. I spent the first talk talking about the problem of quantization and how, to many people, it's framed as a search for a method of sending functions of your position in momentum variable to an operator on some Hilbert space that satisfies a list of 5 axioms that I said was too good to be true. You can't satisfy all 5 of them. You can only satisfy at most 2 of them, because any 3 of them were mutually contradictive. So that paradigm of thinking that there is a problem of quantization and having these list of axioms to look through is it's a very mathematical way of doing it that I believe has arisen as a result of the Schrodinger picture being the more popular one pedagogically to introduce people to quantum mechanics. Because in the original Heisenberg picture, there wasn't really this question, because Born and Jordan, the people who wrote down the Heisenberg picture the very first time, they gave with it a way of quantizing. They didn't use those words, obviously, but a way of ordering operators so that you had a particular choice for how to send P and Q to something, or products of P's and Q's to something that acted on your Hilbert space. So really, the fact that the Heisenberg picture isn't more popular, isn't more well-known, not necessarily pedagogically, but isn't sort of something that's in people's mind as much as the Schrodinger picture, I think is partially responsible for this idea that quantization using that list of axioms. I keep gesturing over here like they're written here. They're not written here anymore. They were written there, though, I promise. Yeah, if this is a 4-dimensional talk where you can go back in time right over here, then they are totally over here. But yeah, no, it is actually a lot of time to go back. It's been a while since that last talk. But anyway, yeah, so Born and Jordan's original method for coming up with the Heisenberg picture, it had already a quantization method. So they sort of went past those axioms. It doesn't obviously satisfy all 5 of those axioms, but they didn't have those axioms as a guiding place to start from. They didn't start with the same question of quantization that we did. They started with more physical considerations that led them to that perspective. So they started with Heisenberg's original picture and his ansatz for what you should be looking for in a quantum theory. And then they had their own ideas. They had, well, not necessarily their own ideas. They took the quantum condition of the old quantum theory that existed at the time, and they sort of rendered it in the system that Heisenberg had then set out. So I'm going to explain that. But first, I want to derive the Schrodinger picture, because I wanted to sort of spend today doing a little bit of a derivation of both of these different pictures. Just because I think it's interesting, I think it's something that other people will find interesting, and it gives an impression of like why this idea of the quantization question arises from the Schrodinger derivation. It doesn't really have a whole lot to say on how you should choose these operators. All right, so Schrodinger picture. So we start out with the idea of a wave packet. Where Schrodinger, we believe that particles are really waves. Things everywhere are really waves. And so somehow our new representation for what we're going to be studying, instead of the trajectories that we're used to, is somehow going to be, goodness, I know how to draw integral signs, and it's not like that. So some amplitude over my k's, and I'll just leave it ambiguous for the moment. Kx minus omega t dk. Okay. dk. So this is a linear combination of plane waves with different amplitudes for different wave numbers. And they represent a bunch of waves moving with the same dispersion relation if you have, in addition, that all of the frequencies are some fixed function of the wave number. So this is a linear wave with dispersion, individual plane waves that make these guys up, which are these complex exponentials with these linear terms in them. These guys don't disperse. They maintain their exact shape no matter how much time goes on. But if you have a nonlinear dispersion relationship here, so this depends on k nonlinearly, then waves that start clumped up together will start to spread out, and so on and so forth. So this is just a way of writing down, a mathematical way of writing down certain types of waves. And so this is the representation that we're starting with for a Schrodinger picture, and we're going to combine that with the observations of Planck and de Broglie. So two people also at the beginning of quantum mechanics who give us that. So this one's hopefully familiar to people who know anything about quantum mechanics. The idea that h bar times the frequency is equal to energy. This is the Planck relation. This is what he writes down as his ansatz when trying to come up with the spectrum for black body radiation. So we have a replacement here. And we also have from de Broglie the idea of matter waves, the idea that particle and matter more generally, you can represent it as a wave. And if you were to do that just by using using tensors and stuff, the idea that these things have to transform a particular way as space-time tensors, you get that the only real choice that you can make that makes sense is this, so times momentum, or is equal to momentum. So the momentum is the wave number times h bar, and the energy is equal to omega times h bar. So I can go ahead and make a replacement. H bar here, and replace k with p, and omega with e. And now asking that they have this sort of fixed dispersion relationship here is just asking that the energy depends, in this case, only on momentum. So this is a valid starting place, really only if we're talking about something like the free particle Hamiltonian, because in that case we can say something like this, like it's equal to p squared over 2m. There isn't a spatial term over here that depends on x. If that were the case, then we wouldn't necessarily be able to use this plane wave decomposition anymore. And that's sort of what Schrodinger, okay. Exactly, there are factors that are affecting these harmonics, these plane waves that are sort of representing like the fundamental solutions to your equations. But this is great now because, in the very least, in the case of the free particle, I know what the dynamics should be, right? From de Broglie and Planck now, if I go ahead and write this in, oh, and also I replace these here. I haven't determined precisely what it is, but this is now looking a whole lot like a general solution of a differential equation. You know what, actually, I'm going to write those up here so I don't have to get rid of them, but I want to take that space still so that I can use more of the board without erasing things. Ooh, goodness me. Okay, so now differentiating this thing with respect to time, we get that this quantity times I h bar, so minus I h bar, I don't know why I put that there, h bar, and p squared over 2m. Okay. And on the other hand, if I take the second space derivative, then what I wind up having come down instead, so I'll get another p squared, but now I'll wind up with just minus p squared over h bar squared. Okay. And now by pulling out constants and then seeing what matches, you write down, or at least Schrodinger writes down, the free version of the Schrodinger equation. So this is the free Schrodinger equation. This is what applies to a particle that isn't subject to any potential, any outside forces. So minus h bar squared over 2m second space derivative. So there we go. Starting with that wave representation and using the de Broglie-Bohm relation, we find out that the free particle evolution that follows from those assumptions is governed by this equation. And, okay. This solution, yes, this is a unique solution to the, well, subject to certain growth conditions on it. It turns out that from my recent time with Cobinson studying analysis, the heat equation and other equations of this form actually have some pretty awful solutions. You can find solutions which are 0 as their initial condition, but it's not non-zero at time in the future.
As long as they grow really
Exactly. It's these incredibly fast-growing things. And so as long as you limit the growth into the future of your function, you can get rid of them. And in general, for heat, you might not necessarily be able to do that. But for these guys, you have some reason why you might say their growth is certainly constrained, because you should be able to square integrate them. But anyway, going on from there, if I go back and look at these representations, and I take this operator and act it on it, then what comes down, and if I just had an E here, if I hadn't made that replacement yet, then that E would come down and be right here. It would have been just like all I would have done is multiply the amplitude function by the energy. Acting this operator on one of my functions is the same as multiplying the amplitude by the energy. And similarly, this is now, when I make the requirement that this is true, then this is just another representation of the energy. But if I don't make the requirement that this is true, then this is still giving me multiply by the energy, so it's still reasonable to call it an energy operator. And this still gives me something that looks like the kinetic energy expression. If I act on it, something like that will come down because of this guy. And so it made sense to Schrodinger to just say, and a potential term will then just be a multiplication operator in X that acts on C added onto that. Because now this looks exactly like the form that we normally see the energy in, at least in classical physics, which is the kinetic plus the potential. So here we have the energy operator equals a kinetic energy operator plus a potential energy operator, and we have the full Schrodinger equation. And so there we go. We arrive at the Schrodinger equation, which we could, if we wanted to, write this operator as H, calling it a Hamiltonian, because why not? If we do that, we can formally integrate this equation to learn that its solutions are given by, formally. Like I defy you to write that thing down for a hard H. It's not going to be easy, but formally you could always write their solutions down this way. If you act this operator on that guy, the H will come out. So, but what you learn from this representation is that time evolution is unitary. And so the square integral of this fellow is conserved. It's a conserved quantity. So if it starts out to something, it stays that thing. And so if it starts out as 1, making psi squared a valid probability distribution, then by evolving according to the Schrodinger equation, you stay a valid probability distribution. And so the Born interpretation comes along and says, we interpret the integral over a particular region of the absolute square of this psi to be the probability that we measure our particle in that region, and the Schrodinger picture evolves from there. But one of the things you'll notice from this is that we didn't come up with, and we didn't really need an exact recipe for how to choose what operators were given by different combinations of p's and q's when we drove this equation. It just didn't need to happen in order for us to get here. We kind of knew enough stuff that that wasn't necessary. And so the Schrodinger equation and the Schrodinger picture derivation doesn't really have any light to shed on the question of which is the correct quantization to choose. And that's sort of why going to future generations, people ask, including Hermann Weyl, which is the source of the Weyl quantization that I talked last time. You go through the Schrodinger derivation. You're now posed with the question of, all right, how do I do this exact same dance, but for a general Hamiltonian that's written in terms of P and Q? And he gave the Weyl quantization method as like a most obvious, easy answer for something that's linear and sends the momentum operator to what you expect it to be, the square root of this. It sends that to that. And that to multiplication by that. So it worked the way that you wanted to, and it was sort of the simplest thing that he could write down with Fourier analysis. And now that we have a Weyl quantization, now you have two different quantization methods, and people have to ask the question, all right, which is the right one, and people are off to the races. And now it's an entirely mathematical thing, and it's very, very far away from the original physical motivations, which are more readily accessible in the Born-Jordan quantization method in their derivation. So let me talk a little bit about that, about their starting point and how it looks a little different. So Heisenberg. Let's see if I can actually manage to fit everything on two different boards.
So is there no like theoretical physical observations that could decide this question?
Which quantization is right theoretically, or?
Yeah.
So people have proposed different ones. I wouldn't be able to tell you whether their propositions could actually do it or not. But there are people there who are thinking about it. It's not something that's been done yet. So at the moment, we don't know. Like we don't have a hard and fast experiment that says, okay, yeah, you definitely can't use that quantization method because it's the wrong one and this is the right one. But we do have, again, the story for where Born-Jordan quantization comes from gives it the most physical relevance out of all of the quantization methods. Any other quantization method that someone has come up with, it's been derived to satisfy those two of those 5 axioms that I gave you. But Born-Jordan was derived from a heuristic physical principle, and it just happened to satisfy those axioms later. So that's the idea. Is no, we don't have an experiment, but between all of them, only one of them has really tried to have a physical motivation. So. Okay. So we have a different starting point. You'll notice about derivations of quantum mechanics, and I guess I don't have any other ones to show you, but I suspect that more broadly this is what's going to apply. It will begin with some new idea on what your representations for the things you're studying are. And then after that, you'll need some sort of quantum condition, some way that h bar enters into the story. So the mathematical representation bit, for the benefit of the audience, because that seems a little vague, in classical mechanics, we're used to a mathematical representation of like a particle, say, just being a trajectory in space. So a function from the real line, or maybe a subset of it, into 3-dimensional space with like the Euclidean metric. But that's just a mathematical object, something that you can describe with mathematics. It encodes information, and as long as you can, at the other side of it, extract the physical data that you're trying to calculate, it doesn't really matter how much it corresponds exactly to what you're used to. The mathematical representation for doing a physical theory is only as good as its practicality, how much you can actually derive from the theory. So that's why, starting from going from a particle trajectory to something that seems obviously counterintuitive, right, a wave representation, that's totally fine if I can still end up calculating the things that I'm trying to calculate in the end. And similarly, the Heisenberg ansatz is to start by assuming that what position and momentum are, so he's still thinking in the Hamilton system of classical physics, where you have your phase space and your position momentum. So he's thinking that the only things that you should actually have in a true proper system of quantum mechanics are quantities that you could actually, in principle, observe. So V, N, M, and then T here. So there we go. So things that you could, in principle, observe. So in this case, something like the position and the momentum got replaced with matrices that contained the transition probabilities, the probabilities of transitioning from n state to m state, and the frequencies of that transition occurring, because those are the sorts of numbers that you could actually measure in a lab. So because those are the things that you could actually measure, Heisenberg said that those should be the things that your representation is made out of. That's the whole philosophical principle behind his ansatz. So you wind up with these sorts of things, or, you know, in more generally, God, I keep doing that, I don't know why. More generally, I could do G for a general observable. It will have exactly the same thing. It will be, you could have it be a function of Q and P, but ultimately, at the end of the day, what it would end up being described by is a matrix. Over the same frequencies. N, M. Okay. So now, so there's our representation, right? Just like we started the Schrodinger picture off with something like this, we start off our Heisenberg picture, or at least the derivation, with what our objects are now supposed to be. Instead of trajectories in space, we have these collections of matrices with these oscillating coefficients, and their oscillation rate is determined by the frequency at which these transitions would occur. Okay, so now where's the quantum condition going to wind up? So it doesn't arise precisely this way. Born and Jordan make a couple of other assumptions, but really what it ends up leading to that's important is that H, we have an H operator here still, and that it is, in this case, for the one that I'm starting out with, a diagonal operator, and that Vm, so H bar Vnm is equal to Hn minus Hm. So if H is the Hamiltonian operator, so it's the operator which is giving you the energy, it contains the energy information. Along its diagonal, that represents the energy of the different states, because it's a diagonal operator, and that's the only place its information can be. That's the only thing that information can be. And now, what this is saying, this is just the Planck condition. What is H bar times the frequency? It's the difference in energy level between those two states. The energy difference, the amount of energy that was lost or gained or, had to change in order for that transition to occur. And so from this, and this obviously implies.
So it's just that written in language of things that can actually be like
acted on matrices now, yeah. Exactly. It's just it's this same thing, but now relevant to this representation. And it's the second part as well, that this is H of just Hn, and then delta Nm. So that's, in general, what a diagonal matrix will look like when I write down its coefficients like that. It'll have a delta function component there, because what that delta function component will do is eliminate all of the off-diagonal terms. Whenever n and m are not equal, that thing will be 0, and it will be 1 whenever n and m are actually equal. So it will only exist on the diagonal. And so from here, from this representation alone, it doesn't take anything more than your very first introduction to calculus to learn that the time derivative of this guy, just going through, these don't depend on time. So we take the derivative of that guy. And, actually, I should, Yeah, no, I should have this because I want to get rid of, it's either, they use h here, and it's either h or h bar. One of these choices is going to make the 2 pi go away from this equation, but I don't remember what it is off the top of my mind. Just know, for all of you out in the audience, that h bar was created, it was brought into existence to get rid of all of the 2 pi's that wound up showing up in formulas. So use h bar and you won't wind up with them, and so that's what I'm going to do here. If you go ahead and actually, you know what, I can go ahead and calculate it. So if I just act g on h here on one side, so what that will end up doing is I will end up contracting the coefficients that are together, so it'll be sum over sum L, and then it'll be G n L e to the I 2 pi e n L t h. This is going to be, yep, L. Okay, that looks big and horrible and scary, but there's a delta in there, so what that really means is that only one of these terms actually matters. It's the one where L is equal to m. So what that ends up giving us is Gn m. I'll bring h out here, h m, and then I'll have e to the I 2 pi. Oops. E n L t. And this, yeah. So this is just a number times that. But this is important because if I go ahead and take the derivative of this guy, and excuse me, if I did this in the other order, I should write it down as well. If I did this in the other order, I'm not going to make you sit through me doing it. But instead of having hm here, I just have hn here. So it would just pick up the other index of energy. So G, can you guys see this all the way over here? Okay. M e to the I 2 pi v and m. Okay. So I have this energy operator, this thing happens, and as a result, the derivative of g here with respect to time is just going to have this guy pop down in front. But when that happens, so I 2 pi v n m g, recalling that this is true, I can go ahead and now make this replacement. So g, I don't have to rewrite that. This is equal to now when I go and replace.
Sorry, the V of n L in this one, the having the L should be something the first one.
V of n, oh yeah, this should be an m. You're totally right, thank you. Yep, exactly correct, yep. So yeah, this now in light of that formula over there, so I 2 pi over h, and then now the difference, so hn minus hm times g. In other words, the difference of these two quantities right here with, now this is I over h bar. Like I said, its job is to get rid of these 2 pi's. And now on this side I have, it's equal to hg minus gh. So there we go. Here's the very start, the start of things. All things evolve based on Heisenberg's ansatz and the Planck condition here, the energy relation from the Planck condition. All things evolve according to this equation. Your time derivative is equal to this thing, which hopefully, if you remember the first talk, that's the Hamilton, that's Hamilton's equation of motion. So I will have to start erasing things because the Heisenberg picture is going to take up a lot more. But this is the last we'll see of the Schrodinger picture, so get a good look at it. But so from here, what we're going to do is introduce, because so far I haven't had to bring up operators at all, right? So far I have well, technically these matrices are my operators, but I have these matrices, and I've gone and using my quantum condition, I've said exactly what their equation of motion should be. But now, how do we know that we've wound up with the right equations of motion? How do we know that this is going to describe physics as we know it? Well, Born and Jordan used something called the correspondence principle, which I'll explain more closely once I've gotten rid of this. The correspondence principle, though, it's roughly a heuristic for going from a classical theory to a quantum theory. It's not an actual hard and fast formal rule. All it is saying that your quantum laws, whatever they are, should look like your classical laws. So since we remember hopefully from last time that our laws for motion in normal classical physics were this. And then dot is equal to minus. These are Hamilton's equations of motion for classical physics. And what Born and Jordan do is they say, all right, I have functions, my H, my Q, all these guys. These are matrices now. They're not real numbers. But I want them to satisfy this same equation. And if I want that to be true, then there's only one thing that can happen. Looking at this, right? G could be Q or P, anything, right? G is general. So we know they satisfy that. We want them to satisfy this, and hence I need this to be true. I H bar is equal to, H P minus P of H, and then is equal to I H bar, because that's the only way that or excuse me, Q. Yeah. I took a step back and tried to make sure that I wouldn't mix them up in my head, and I'm pretty sure that's precisely when I mixed them up in my head. What happens to me all the time. But there we go. So these are sort of the requirements that need to happen in order for the correspondence principle to be fulfilled. In order for us to have equations of motion that resemble the old Hamiltonian mechanics, I need it to be the case that somehow taking partial derivatives with respect to the momentum is the same as doing this action, and taking partial derivatives with respect to space is somehow the same as this action. Or, by the minus sign, technically, it would, with this swapped, but who's counting? So there we go. So how do we go about achieving that? Well, it turns out that for functions h of the following form, it's really, really easy. So Q, P is equal to power series, J is equal to 0, L is equal to 0, infinity, AJ, PJ, and BJ, QJ. There we go. If I just have a Hamiltonian that looks like two different analytic functions, two power series, which are separated in the Q and P variable, then it turns out that from this relation, QP minus PQ equals IH bar, from this we can go ahead and derive, so this, by the way, which is commutator Q acting on P. We can go ahead and derive from this that which is almost what I have here, or rather, yeah, this is similar to what I'm going on here. Some of the things that I'm about to write down here might be correct modulo a sign flipped, because I'm going to be forgetting that. But the idea is that now if I go ahead and start increasing powers, and you can derive it from this relationship. I'm just too lazy in my head right now to do the commutations on these things. But you can get that n by h bar p to the n minus 1, and similarly, and any formula that's true for this guy will be true when you exchange p's and q's and replace h bar with h bar minus. So I can just go ahead and p q n is equal to minus n by h bar q minus n. And now I know, remember what we're trying to show. We're trying to show that the partial derivatives coincide with these commutators, with the different variables. And what we've shown here is that commuting qn with p takes q's derivative, right? This is exactly the power rule. I've got the n showing up here. I've got the n minus 1 there. So as long as I have you split like this, remember a commutator is going to commute with itself, so this part will just be 0 when I hit it on that, just like if I acting a partial derivative in q on a function of p. So this, something that's represented like this, just by linearity, will necessarily have the property, so this is I h bar minus I h bar derivative with respect to q, acting on qn. But in general, for one of our h's here, if I go ahead and take his commutator with p, it will just give me that, just by linearity. Awesome. So as long as we only want to talk about Hamiltonians that look like that, we don't even need to pick quantizations. But that's something that we already talked about last time. So this is... Exactly. It's entirely a contrived thing. You can't necessarily expect that your Hamiltonians are going to look like this. And in particular, if you're talking about relativistic Hamiltonians, they can't look like that. You will never be able to separate them if you're talking about something that's like properly relativistic, Lorentz relativistic, I should say. Technically, all things are relativistic. There might be Galilean relativistic, but okay. So there we go. So far, we're going off and we want these equations to be true, but it looks like as long as we're taking really simple Hamiltonians, that's always going to be the case no matter what. As soon as we start incorporating Hamiltonians that have pieces that look like this, though, P and Q, excuse me. This won't be true anymore. It won't be the case that we'll be able to get this to work out. The formulas for taking partial derivatives, which Born and Jordan write down, I might as well write them down here somewhere as well. Born and Jordan write them down in their article, show up and are necessary in doing this computation. But yeah, you basically find out that for things that involve non-trivial mixed terms, unless you do certain reorderings, you just won't get this to work out anymore. And since this is the guiding principle that Born and Jordan are using to determine that their equations make sense in the first place, they say that we can't just proceed onward if we're given a Hamiltonian that looks like this. If someone hands us that Hamiltonian, then we have to call that Hamiltonian star and say that we're not done yet. We want something that has the same equations of motion here. It gives you the exact same this guy, but this now ends up working for it. It turns out that all that you need in order for that to be true, just in light of looking at what's going on with this equation, is you just need the partial derivatives of this guy with respect to the different operators to coincide. So I want some new, and this is, by the way, why if you go and look at Born and Jordan's original paper on this, on quantum mechanics, you won't see anywhere them say, and here's our quantization method. They didn't even frame any of what they were doing in terms of taking functions and then replacing them with operators. They were taking already existing Hamiltonians, functions of operators, and reordering them so that their equations made sense. So technically, the reordering that we call Bohr-Jordan quantization is implicit in their paper, but yeah, they didn't consider it. They weren't characterizing it that way. So again, and the same thing for P. I'm just not going to write it down. But yeah, so you want to find one of these H's that has this property so that the equations of motion make sense. And Born and Jordan say not only can you do it, but other people who've come afterwards, Maurice A, Gosson, who I mentioned in my abstract, whose work I'm probably not going to get to because it's already taken too long to get what I've gotten to so far. He has gone on to argue that it's actually the unique choice that realizes these constraints that he's made. So not only can you come up with the H that he wants, but it's the only one that you can come up with. So I'm going to go over here now and start writing down the procedure. And this is where I'll wrap up today. I'll wrap up here and then, because we're already at the top of 5, and I'll let you guys go. Because we don't need to spend forever doing, yeah. I know, I've been torturing you. Okay, so yeah, I won't spend too much time on it, but basically they take this product and say if you replace every single one of these in a linear fashion with the following average, so this is where their idea comes from. They're taking an average of a bunch of different reorderings. So n plus 1. J is equal to 0 up to n, p n minus j, qm e to the j. So,
Bryce, do you want to stop right here for a second? We'll just switch paths.
Yeah, sure.